Hello, I'm Haraken. So nice to meet you again. So are you excited? Great. So this is the second lightning talk session, and I have the second party popper here. And also, so I prepared a big sheet here so that I don't need to clean up later here, right? Okay, so let's set it up here and let's try. 1, 2, 3, blink on. Oh! Okay, so it didn't work well. So, but are you more excited? All right, so party popper significantly increased your excitement level. So this is great. All right, so today, we will have 10 lightning talks, and each talk is 3 minutes long. So if you are a speaker, please come to the front and make sure to finish your amazing presentation in 3 minutes. Is that okay? All right, so let's get started. The first speaker is Gyu Yang. So go ahead.
Hello, I'm Gyu Yang from Italia. In this talk, I will give you a brief introduction to the Blink for Apple tvOS project. We started this project for several reasons. First, Apple TV is an Apple platform that runs tvOS, which is an iOS-based platform. However, tvOS doesn't provide the wiki depots. This means that application developers who need a web functionality should include their own web components. For example, YouTube has used been custom web engines called the Cobalt. Cobalt on tvOS is based on outdated and highly stripped down Chromium Pro. So the maintenance burden keep growing and becoming more difficult. Next, the BlinkGen project was launched. BlinkGen was the project name of Blink for iOS. So BlinkGen has been developed as an experimental project. If you are interested in the BlinkGen project, you can take a look at the slide in the BlinkOn 1919 talks. So, and we saw an opportunity to explore porting it to tvOS. Additionally, we considering the possibility of upstreaming of Blink for tvOS. For these reasons, we believe that it was worth trying. While porting it to tvOS, we encountered several challenges. Because the tvOS is an iOS-based platform with a unique quirk and limitation. So we are not targeting a fully fledged browser on tvOS. Here are some the difficulty importing in Blink to tvOS. First, tvOS does not support multiprocess application because some low-level system API required for the multiprocess application are not available on tvOS. Then, so tvOS does not support the browser engine kit that BlinkGen rely on to support the multiprocess and JIT. Even JIT is not allowed in Apple App Stores. Lastly, the Apple TV Remote is the primary input method, and it is very different from the keyboard, mouse, or touch-based input method. Now, let me share our current progress. To launch your content shares, we have made several key modifications. First, we add a new toolchain and build flag. In C++ and Objective-C file, we have used the iOS on the tvOS build flag, and also we introduced a new target on the platform GN variable for GN checking. And also, we enable single process mode because I said the multiprocess is not supported on tvOS. And we apply the GN and build flag to the third-party libraries such as Angular, V8, and Down. And also, we have excluded all code which depends on the browser engine kit. Also, we disable the JIT in V8. And we have been disabling unsupported low-level system API in upstream, so we are still in progress. And furthermore, we have been supporting hardware accelerated graphics and codec and crashpad, and we're working on improving the handling. Yes, here is a simple demo playing a YouTube video in content share on the Apple TV simulators. Yes, he's a J-Hope, who is a BTS members. Yes. Yes, we still have several tasks ahead. First, we need to finishing merge downstream patches to successfully build and learn a potential in upstream. After that, we plan to set up a reference board to put up tvOS there. Lastly, we will try to patching the relevant unit tests, browser tests, and web tests. That's it, and huge thanks to all review and sponsors for this project. Thank you.
Thank you very much. So the next speaker is John.
Hello, BlinkOn. I'm John Xu from the YouTube Cobalt team, and I'm here to tell you about our new project, Cobalt. So first, let me tell you a little bit about our history. Cobalt was a HTML5 mini browser for smart TVs. YouTube is Cobalt's biggest web client. Cobalt has a few hundred million users. It's lightweight, it's fast, it can play 4K video on very cheap devices, and it's very portable. We supported a dozen different platforms. But on the downside, it is very limited in web API support, which is the main motivation of our new project, Cobalt. And the idea is very simple. We take Chromium and we make a single tab browser out of it. Chromium is going to give us WASM, iframe, all these production-ready implementation of the APIs that we have wanted for a very long time. And we're going to drop our custom browser component. We are fairly confident that we are going to make it performance on par, but we're sure to lose some portability. But though that might be fine because the TV market is really converging towards Linux and Android-based operating systems. And now we are ready to take a look at the architecture differences. You can see in the old app, we have our own layer of web implementations. Underneath it, we have our own custom renderer and a custom media player. And we borrowed a ton from Chromium. And all of that was implemented with our own platform abstraction C interface called Starboard. Moving on to the new world, we started from content shell. We're gradually transforming it into an embedded app of ourselves. It's still single process. We kept our media player made for smart TVs. We introduced custom APIs, custom security policies, lots of mini surgeries, and it totally worked. We are almost ready to hit production. We're talking about Android now. So a natural question is, why don't you just use WebView? Well, we really tried, and we talked to WebView team and Conk team extensively, but we don't know how to cleanly make encrypted content play in an overlay. My colleague Boron is going to talk about that in a few minutes. And we don't really have any native components outside of the WebView. So the synchronous compositing and rendering is not really going to give us any benefits. On the next steps, we're going to roll out the app on Android TV and see how it performs in production. We have tons of optimizations planned. We're going to make the app work on Linux and tvOS, as just introduced by our friends from Igalia. And last but not least, we're going to work with people in this room to see how much we can contribute back to Chromium. Our code is fully open sourced. Feel free to take a look at our code and documentation. And also, if you have Android TV at home, feel free to join our public dog food. Thank you.
Thank you very much. And the next speaker is Boron.
Thanks. Hello, everyone. My name is Boron Chen, and I'm from YouTube Cobalt. And today I'm going to talk about Cobalt Media. So before diving into today's topic, I want to quickly recap what Cobalt is. Cobalt is a HTML5 web runtime for smart TV and game consoles, and it defines a layer, it defines a platform abstraction, which we call Starboard, and provide platform-specific functionalities to allow Cobalt to run HTML5-based video across different platforms, including Apple TV, Linux, and Apple TV. And inside Starboard, the parts related to media contain many YouTube-specific customization and optimization to living room devices, which we call Starboard Media Player or SB Player. So the benefits to bring Chromium and Cobalt together give us the following benefits, like MSE in workers, fully feature web audio, well-defined sequence of events, and unlock future enhancement like web codecs or WebRTC. But the challenge for us is how can we bring this self-contained starboard media player to Chromium? Compared with a Chromium media diagram, the parts below this line are actually the job belong to starboard media. So for Cobalt and Chromium, we will still use the same media pipeline, but all the video rendering and decoding are actually inside starboard media. So for the video rendering, there are typically two ways. One is when we get a video frame from video decoding, we can actually convert this video frame to a OpenGL texture and draw this texture on top of service texture. And this is called texture mode, which is used by Chromium by default. And the other way is we can render this video frame directly on a service view. And this is called video overlay mode. And this is used by Cobalt by default because this is more efficient and support encrypted contents. So this brings us a two-layer issue where for the Chromium, all the web UI are drawn on a layer which is called a Chrome composer. And we have another layer owned by starboard media player to render the video. So if we put starboard media player on the top, Chrome composer on the bottom, the video will block all the web UIs. On the other hand, if we put Chrome composer on the top, starboard media on the bottom, the web UI will block the video. So this is one of the examples when we put starboard media player on the top, Chrome composer on the bottom, we can see the video block all the web UIs. On the other hand, if we put Chrome composer on the top, starboard media on the bottom, then the web UI will block the video. And notice that the web UI here should be semi-transparent, but it still blocks the video. So the solution we have here is we can punch a video on the Chrome composer so they can work together with a starboard media player. The way we did this is by we put starboard media player on the bottom and Chrome composer on the top and make this Chrome composer transparent with a video whole frame. So the video rendered on the bottom by a starboard media player can still be seen through all the web UIs. And this is a demo to show how they can work together. And notice here, for all the web UI, they are semi-transparent, so we can still see through the video rendering by starboard media player. So the next step is next step is we will improve performance in production and support more video mode like media texture mode, more platform like Linux, and then upstream all the media, Cobalt media optimization to Chromium. And thanks for everyone.
Thank you very much. So, and the next speaker is Michael.
All right, thank you. Do it this way. All right, so I'm Michael, and I work on the Chrome Speed Metrics team, and we help measure the performance of the web, among other ways through a program called Core Web Vitals. So as users navigate through the web, we try to record the quality of their user experience, and we aggregate into a simple set of scores shared with site owners. So how do users navigate the web? Well, on desktop, about 1/8 of navigations are for new tabs. And this often includes browser session restore, and these tend to be the slowest to load. About 3/8 of navs are cross-origin, maybe from search results, and they tend to be a little less slow. And about half of navs are same origin. And so these tend to be faster. On Android, the distribution is similar, though there's a larger share of new tabs. There are also these things which are effectively navigations, though they're technically different. BF cache restorations and pre-render activations, so we're trying to drive up these numbers, and these tend to be the fastest. But there are these soft navigations as well, where the website owner decides to handle things entirely themselves with JavaScript. And on desktop, we think there's like a bonus quarter of navs that are soft navs. And these are currently not measured. Are they fast? We don't know. We're trying to change that. So we're intending to measure soft navigations, which are initiated by a user interaction, and only when that interaction directly leads to two things happening. The page content is updated in meaningful ways, and the URL is changed to represent that new state. So the goal is to figure out, when are those effects I just mentioned caused by that interaction, even over time, even across asynchronous scheduling? So the idea is we'll establish a new context with each interaction, and we'll try to keep track of it across time. Certain event listeners are assigned this new context by default. Then each async API they request, like a fetch or making a scheduler call, will keep a reference to that context around. Finally, each continuation, like a macro task or micro task, will restore the context before execution. Then, within each task, at any time, you can grab a reference to the current context. So it's like a bit like local storage or thread local storage, but for our single-threaded scheduling flows. So currently, this is an internal capability within BlinkOn V8, but there is a parallel effort called async context in TC39. I think there was a talk about it last year, and this aims to expose this feature to web developers to the web platform. So now, when we observe effects like DOM modifications and URL changes, we can attribute those effects back to that original interaction through the context. So by understanding the scheduling of the tasks that created the effects, and because we have this persistent context. Finally, we can map interactions to attributable paints, things users actually see. So although the paint stage of rendering is not itself task attributable, it doesn't have a context, we know which DOM modes we're painting, and we can map from paint to node to context to interaction. And we also have a prototype that leverages container timing. You heard about that yesterday, which does an even better job of tracking paints. And so here's what it all looks like when it comes together. Hopefully the video starts. Here I'm interacting with pages that are sort of single page apps, and it's visualizing parts of the page which were changed by that interaction in ways that we can attribute right now. We're working to continue to improve. So with this feature, and a few more simple heuristics that we layer on, we can begin to report a soft navigation timing entry, which will provide website authors with a new start time for a type of time origin, as well as new contentful paint entries, which will provide loading performance insights. And there's probably a lot more we could do than that. So thank you very much.
Thank you very much. And the next speaker is Orko.
Hi, I'm Orko from Igalia, and today I'll talk about Ozone Wayland. So in Linux, we have two backends for Windows system integration, X11, which is the current default, and Wayland, which is the native Wayland backend. Many users are currently using it. Today, I'll talk about some of the recent developments there. Per window scale is something we implemented to support scaling on high DPI displays and fractional scales. We implemented text scaling for large text accessibility feature. We experimentally implemented text input v3 for IME use cases. We have full Chrome tab dragging UX support via a top-level drag protocol, which we upstreamed in addition to implementations in Mutter and Chromium. And so now it's working in GNOME 48 and KDE. We also have a tab dragging UX for a simpler UX for alternative compositors that don't support top-level drag. We implemented explicit sync for fixing screen tearing on NVIDIA GPUs. We have session management, which recently landed for restoring windows in previous positions and workspaces. And we did a bunch of other fixes, including window focus issues, rendering issues when window is obscured, and window manager favicons. We also have a couple bots that are now running tests on Mutter. And for future work, we plan to support IME fully, always on top picture-in-picture windows, VRR, hardware overlays, and graphics tablets. and here are some demos. This is text input v3 in action. This is top-level drag. This is fallback tab dragging. And finally, many thanks to all my colleagues at Igalia and Chromium. Thank you.
Yeah, thank you very much. And the next speaker is Sang Yang-sun.
Okay, I'm Young-Soo Choi from Ozone Electronics. I'm going to talk about how we reduce the memory usage by downsizing the Chromium library. Oops. Oh yeah. So these days, most of devices have plenty of run sizes, but the embedded device like smart TV still have less memories. The problem is that Chromium is huge, and you can see that Chromium library size is more than 200 megabytes. However, what matters for the binary size and the memory usage, you can see the how much memory is used to load the text segment of the library through the memory infra tool of the Chromium. And if you open the files column, you can see that more than 40 megabytes was used to load the Chromium library in WebOS. So the text segment of the library is a huge portion of the memory usage. And we can assume that if we reduce the binary size, then the memory usage can be reduced. So how can we reduce the binary size? There are several options for it, but I already have applied other options, and I'm going to talk about the last option, removing the unused features. So if we remove features from the library, then the corresponding size of the binary is reduced. For example, if you remove Chrome extension feature, then 9.3 megabytes is reduced, and for 7 megabytes for web GPU and so on. And I'm not saying that we're totally not using all the features here, but just adding options for it. So if the feature is not needed, we can exclude it from the library and save some memory by it. And what about the memory usage then? This shows the result of the memory usage by reducing the binary size. The red line shows the memory usage when all the features are removed, and it shows that about 10 to 20 megabytes was saved by removing the features. So our team have proved that if we remove features, then the memory usage could be reduced. But removing features was not that simple. These were some issues we met. First, Chrome extensions was not able to be removed by default. And for Chrome trace events, it seems there is no direct disabling flag for it. And most of the feature doesn't provide some build excluding options, only like disabling options. And one of my suggestions is that there are many experimental features and runtime enabled features in Chromium, and it'll be better if there are some options to exclude it from the build. Okay, that's all. Thank you.
Thank you very much. And the next speaker is Sahir. Yeah, great. Thank you.
Hello, everyone. I'm Sahir from the Edge graphics team, and today I'll be talking about removing the Chromium redirection bitmap on Windows. So over the last couple of years, we've gotten several reports of frustrated consumers talking about a big white flash that happens as soon as you start Chrome or Edge, and it's caused a lot of frustration. And so here's a demo of the flash. You can see this white flash, and if people are sleeping or using the computer at night in dark mode, they hate that. So the source of this flash is something called the redirection bitmap. So Windows allocates one to every top-level window, and it is used as the surface which GDI and DirectX can render to. So what happens during the flash is that the window is created before like the first compositor frame is submitted to the GPU process, and so this white placeholder is shown. And so to eliminate this white flash, we can remove the redirection bitmap. However, it is not trivial to do so because in software mode, Chromium uses like GDI APIs to like bitblit content onto the redirection bitmap. So we have to replace GDI with using swap chains and direct composition. And what that does is not only does it allow us to remove the bitmap, it brings parity between hardware and software mode. And DWM, which is the OS compositor, can also render things faster because it can pick up rendering results sooner rather than waiting for all the batch processing commands that Bitblit will be part of with GDI. So with the redirection bitmap gone, we still need to replace it with something. Otherwise, you'll just have a transparent window. So on Windows 11, what we can do is have DWM create a backdrop, and that could be like an acrylic or a mica effect. And that allows us to save memory by not needing a window-sized texture. On Windows 10, that functionality unfortunately isn't available. So we had to build out a different solution using Windows UI composition APIs. So we can create like a tree of visuals of solid color visual, and that can make up the backdrop. So again, this is what would happen. This is a bit slowed down on debug mode, so you guys can see the white flash. And after that's using the UI composition visuals, so there's no more white flash. Thank you. So there is something else. So that wasn't the only source of white flashes. There would also be a white flash that would show up when the window is being restored. And that happens because a like solid colored draw quad would be shown to the screen as the window is resizing, and that quad would be added before when the window is being minimized. And so for that, it was low-hanging fruit, so we could just change the color of the quad to match the frame color. So again, no more white flash when we're like maximizing. So this feature is nearly ready. There's only one thing to do, which is to have it working on D3D9. Older APIs that only 3% of Chromium users use. And those, unfortunately, do require a redirection bitmap. So we can create a child window and have angle render to that. So you can try it now using the feature flags provided. And just like to thank everyone who helped review: Raphael, Sushant, Sunny, Kyle, and Michael.
Thank you. And the next speaker is Rob.
Hi, everybody. Thank you very much. Very excited to talk to you about something that I talked about at BlinkOn 18, which is enhanced traces for DevTools. So this is something that we've been working on now for a while. So I want to tell you a story. Names have been redacted to save people that aren't here. But basically, we got a report, hey, the VP took a trace, and you know, by the time it got to someone, there was a problem in production. By the time it got to somebody who knew what they were doing to take a look at it, you know, the CI had deployed 3 times. We have different files up now, and so it's not easy for us to go back and repro. We can't get this perfect repro because maybe it's some file that they have, or you know, some situation that they've gotten. So it's really hard to get a reproduction here, and so it's really hard for us to also go back and look at exactly what the performance problem is. So there are a bunch of shortcomings with DevTools traces, and as good as they are, they've been really hard to work with. In particular, if you can't get a good repro of the scenario, maybe the script's load in a different order, and because all of the trace events are correlated by script ID, which is an integer that just increments over the lifetime of the trace, it's not always a perfect solution to just, you know, go back and try your best to load up. So realistically, that's a problem. And then the other is that source maps aren't always loaded on demand, so sometimes unminification doesn't work. So what is an enhanced trace? Well, this is that what we've done is you embed your script information, at least the information that was available at the time of running, into trace events. And so now what you're able to do is you're able to recreate a situation, we call it a rehydrated session. Basically, you can pop open a new window that looks and feels sort of like DevTools state would have been if you captured it at the time of the trace. The nice thing about this is that it's not restricted just to being taken by DevTools, because it's all controlled via tracing categories. You can also do this in other scenarios like web page tests, or if you're just using Chromium tracing. So you get a new window that pops up. That new window has the ability to enumerate through sources so that you can see exactly the files that were there. You can optionally embed the actual source text of the scripts, although that's not on by default, because that could lead to a situation where we leak PII. But yeah, so it recreates a subset of the state that existed. It optionally embeds the sources, like I said, and so if you have the source map server extension, which also just landed recently in Chromium, you can also load source maps via an extension so that you can get the exact version of the source map that was present at the time that you took the trace. So, like I said, there's three new tracing categories. DevTools will kind of subclass the connection when you load an enhanced trace to basically, from the DevTools perspective, act as if it's talking to a real debug target, but it's not. It's just talking to itself. And so it gets a set of interactions that looks as if it's there. And so this is how you can try it. In DevTools settings under experiments, go turn on enable collecting enhanced traces. And then when you export your trace, right click on the export button and choose enhanced performance traces. And for future, we're also looking to support this for memory tooling, particularly around heap snapshots. In Edge, we had initially done this in a kind of different mechanism that didn't include using tracing categories. So there's interest, though, about being able to capture a DOM snapshot. It's kind of neat. Also, console messages, also interesting, but we have to consider privacy. And then can we put this into tools that exist in the community like web page test? So thank you. That's it.
Thank you very much. And the next speaker is Leah.
Hi, everyone. My name is Leah. I'm from Microsoft, here to talk about updates to the Web Install API. The current way for users to install web applications can be unintuitive, and it's often inconsistent across browsers and platforms. The Web Install API provides a way to democratize and decentralize web application acquisition by allowing websites themselves to directly install web apps. The first main use case is what we're now calling current document installs, meaning a website installing itself as a web app. Let's install the PWA store. The install confirmation prompt shows, and now we have the app. Note that the document reparented, which is identical to the existing Chromium install flow. The other main use case is what we're calling background document installs, meaning a website installing something other than itself as a web app. This enables scenarios such as stores of web apps or even app installs directly from a search engine results page. We implemented this as navigator.install, a promise-based method with the ability to install web content, provided that its manifest meets certain criteria. Navigator.install now has 3 signatures, 1 for current document installs and 2 for background. The first 2 require the document's manifest to have an ID. The third takes an ID as an argument, but does not require it in the manifest. So why have this third signature, and why does the ID matter? Well, manifest ID is the app's unique identifier. Without it, the browser computes an ID based on the start URL. Unfortunately, as of last check, only about 4% of apps actually declare an ID in their manifest. This opens the door for orphaned apps or even security issues if the developer changes their start URL, as their site will appear to the browser as a completely new app and existing installs won't get updated. The web install signatures have been designed to support widespread API adoption now, while also encouraging developers to add IDs to their manifests over time. Permission is now required only for background document installs. Navigator.getInstalled apps was previously proposed to let an origin request a list of apps that it had installed. This has been cut due to potential privacy concerns, as well as potential confusion with the getInstalled related apps API, which is similarly named but serves a completely different purpose. To wrap up, let's use our newly acquired app, PWA Store, to install something else. Because this is a background install, we're prompted for permission, and now we have the music player. This has already been implemented, but we're still working on showing the install confirmation prompt for this scenario. Our updated API design is undergoing a new tag review, and we're targeting 138 for dev trials, with origin trials to follow. Thank you.
Thank you very much. And the final speaker is Rick.
Thank you. There were 2 open slots. Y'all didn't sign up for enough, so I signed up for a second one. This is a story of my biggest mistakes. At least we only have 3 minutes, so it's only as a browser engineer. And then it's only the ones that were top of mind for me, because, again, we only have 3 minutes. This is inspired by this CV of failures and also a colleague of mine, Glenn Hartman. And I just think we learn more from our mistakes and our successes, and yet we come here and we talk about our successes. So I'm just going to try to tell you some of my mistakes. So first of all, as many of us do, I always underestimate technical complexity. The number of times I said, oh, this looks like it's a quarter of work for this web API, and it turns out to be years. Root scrollers and old example portals, we worked on that for years. Animation worker, we thought this was actually, anyway, lots of examples. And sometimes I say, well, this actually looks big. I know better than to say this is going to be a quarter. It might take a couple of us a few years to do. And that's, for example, when at the very beginning of the Privacy Sandbox project. That's what I said. Turned out it was bigger than that. Okay, number 3. Assuming we reach a point of diminishing returns, when I started really diving into web performance a while back, I said, okay, we've been working on page load performance in Chromium forever. Surely we've got most of the low-hanging fruit, right? And that really influenced the design of Core Web Vitals and the strategy about trying to influence the ecosystem. But what we found is after we built a lot of the measurement infrastructure for Core Web Vitals, it looks like sustainably about half of our wins to speeding up the web have come from Chromium improvements, and half of them have come from the ecosystem improving. And there's been some massive ones that were just like bugs that we didn't know we had until we looked closely enough. So I think that's a good lesson. Number 2, letting lack of consensus block adding a feature to Chromium. My best example here is pointer events. I worked on pointer events for years, and then we decided we're not going to do it. One of the reasons we said we weren't going to do it was we cared a lot about mobile, and Apple said there was no way in hell they were ever doing pointer events, and I believed them. And then we got a lot of pressure from web developers and others in the standards community and whatnot who told us, like, you should do it anyway. And we eventually reversed course and did it. And then 2 years later, the iPad came out with a pencil, and then Safari shipped it as well. So I regret causing all that turn. More recently, device-bound WebAuthn keys. We've secure payment confirmation used to work great and then was broken by passkeys syncing, and we blocked on the WebAuthn group debating about device-bound keys for 2 years when we realized we could have just done this without waiting for them at all, and that was silly. And then number 1, I think my biggest mistake is deprioritizing pragmatic high-level APIs for low-level primitives. And there's lots of good in the Extensible Web Manifesto. I'm not saying it's wrong, but I think I made some big mistakes here. My favorite example is snap points. IE10 had this great snap points feature, and Microsoft did a ton of great work to propose it as a web standard. And then, I spent some time talking with some leads on the team, and I sent one email to WW Style saying, hey, we want to work on low-level primitives like animation worklet and stuff, and maybe we can come back to this later once we have the primitives right. See point number 4 at the beginning. That turned out to be way harder than we thought, and so we basically ended up delaying snap points by 2 years as a result of this kind of philosophical view. And similarly, actually, I forgot to put it on the slide, but view transitions, portals in some way was intended to be a low-level primitive that was super powerful, and Jake Archibald was really pushing view transitions, and I told him, I thought we could get more power out of doing something low-level. So I think the lesson there is just we really should, low-level primitives can be 100 times harder than high-level, and so don't let extensible web idealism block us from putting the pragmatic things first. And that's all. Thanks.
Thank you very much, everyone. So that's it. So 11:41, we are mostly on time. So thank you very much for the collaboration. Okay. So that's it. So thank you very much for coming. So and we will have the final lightning talk session at 2:35 p.m. So today. So thank you very much for coming, and please send another round of applause to all the speakers. So thank you very much.